is a video regarding the Module 8, Cost at Building Level, within the course Economic and Sustainability Aspects of Architecture and Urban Design. Module 8 is registered in several videos. This is the first part. To situate this module in the overall course, we have first investigated and analyzed climate and comfort in different climatic contexts and learned how you can use weather parameters to analyze your climate and how the comfort charts can be used to get an idea of the comfort situation, thermal comfort situation in a specific context. Module 5 to 7 focused on the solar analysis by using solar charts or shadow charts to analyze the solar access to your building and how you can change it by design measures. The next two modules focus on the cost calculation, ending with presenting your results to the group. This module is on the cost at building level, the next one focuses on the cost at neighborhood level. For the cost at building level, we will mainly focus on how the building layouts, the design choices regarding the building size and form will influence the cost of your building. We will not investigate how the material choice influences the cost. This is really very site-specific, country-specific, and is out of scope here. Of course, this will influence the overall cost of your project, as we will see in the next few slides. So when looking at the influence of the building layout on the costs, we need an appropriate method. To do that, we will look at several aspects. The lecture is structured as follows. First, we will look at how we can decompose our building in smaller entities to control the costs. This is done by looking at the element method for cost control. Second, we will look at the concept of ratios. Third, we will make an abstraction of our complex buildings to an equivalent box building. Fourth, we will look at how we can use a tool to calculate the costs to estimate the investment of your building. And finally, we will look at how the investment costs differ from life cycle costs, and we end with some conclusions. This video concerns the first 2 points. We will look at how we can decompose our building in smaller entities and how we use the concept of ratios for checking, understanding the influence of our layout choices on the costs. So first, let's have a look at the element method for cost control. When we look at the design process, it evolves over time. Typically, the design process goes from the programming phase, where the function of the building is determined, where all the parts that are needed to fulfill these functions are defined. In the sketch design, these are further elaborated by taking important decisions regarding the building form, layout, orientation, window to wall ratio, and so on. And further on, the design is further detailed by choosing specific materials, by choosing certain connections between elements, choosing for a certain height of a floor, and so on. We see that during the design process, the available information on the project hence increases. So in the beginning, little information is available, but along the process, the amount of information on the building is increasing. However, what we see on the contrary is that the first design decisions have a big influence on the financial cost of your building, while further on, the later decisions have a smaller influence. They still influence the cost, but to a smaller extent. So the first decisions regarding the big decisions on the size of the building, the layout of the building, will have a big influence on the cost. It is hence important when we want to make an estimation of the investment cost of a building, that we have a method available that allows to make quite an accurate decisions, quite accurate cost estimation in the first design phase. But on the other hand, we also want to further refine the cost estimation along the process when more decisions are taken, and hence when more data are available, become available. So what we actually are looking for is a method to make rough cost estimations in the beginning to support the decisions taken at that moment in the design process. And on the other hand, we don't want to redo the whole calculations from scratch later on in the design process. We still want to build further on the first cost estimations, but refine them along the process when more decisions are being taken. And that is exactly what the element method for cost controls allows you to do. This method is well suited to respond to these both requirements. Rough estimations in the beginning, supporting decisions taken at that moment, and have more detailed estimations later on when more decisions are taken and hence more data become available. So it's a method that allows you to gradually evolve your cost estimation along the design process. The method has been established in Great Britain and has been used throughout Europe. And here in Europe, the Netherlands played quite an important role in the beginning when this method was established. Today it's used by architectural offices, quantity surveyors, engineering offices, both in the Netherlands and other European countries. The two main aims, as said before, of this method is first of all to allow for useful cost estimations very early in the design process and to estimate these costs more precisely along the process when more information becomes available. It is not only a cost estimation technique, it's also a cost control technique. So the intention is that with this method, you can make sure that you don't exceed the budget of your client by checking consistently throughout the process what the consequences of a certain decision is on the investment cost. The element method for cost control basically divides the building into independent building elements. These elements, these parts of the building, are based on their function. And it's also parts of a building that a designer is accustomed to work with. So if we depart from a building, we could divide the building and all its building materials and have a list of kilograms of bricks, kilograms of concrete, and so on. This is possible, but it's not an easy way to make very good estimations in the beginning because you don't know yet your kilograms of concrete or brick, and it does not allow to gradually make more precise calculations along the process, because then you would need to recalculate these kilograms every time along the design process. So what is done here? The building is subdivided in elements like an outer wall, a floor, a roof, and each of these elements has a specific function. Based on this specific function, we can define technical solutions. So each of these elements have a specific build-up to fulfill the function it needs to fulfill. So an outer wall, for example, is composed of different materials, different layers, different work sections, we call them. And each of these layers, each of these process materials has a certain function. Altogether, they fulfill the full function this element needs to have. Each of the process material, for example, a brick wall, is part of an outer wall in Belgium. Typically, this brick wall consists of different materials, the bricks and the mortar, cement mortar. So we can subdivide our building in different elements. We can subdivide these building elements in work sections, and again, we can subdivide these work sections into building materials. This is hence what we call a hierarchical subdivision of our building. Each layer can be subdivided again until we get to the lowest layer of the building materials. We can also go higher up. We can go to the neighborhood level, for example, which not only consists of buildings, but also consists of infrastructure. And we can calculate the cost of the different parts, the different elements in a neighborhood based on their function, and again, look at the overall cost by looking at all these aspects. Now, to make it more concrete, here I show you different technical solutions of two elements of a building. The first are four solutions for build-ups for an internal wall in the Belgian context, and on the bottom you see 3 solutions for an external wall in the Belgian context. The function of an internal wall and an external wall is different, so the build-ups are different. We cannot use a build-up above to fulfill the function of an external wall, because this internal wall, for example, is not watertight. There is no insulation level, so it does not serve the function an external wall should fulfill. So an external wall has a completely different build-up because of the different function it has. By looking at a certain building element with a certain function, we can define the function it needs to fulfill, and based on that we can define, based on the properties of the material, certain solutions, technical solutions. So overall, a building in the center here in the figure is subdivided in different functional, what we call macro elements. An example of a macro element is a floor on grade, is an outer wall, is a roof, an internal wall, and an internal floor. These are 5 different functional elements in a building. There are many more, but I just give you some examples. Each macro element with a specific function gets a different symbol, a different coding, but it's not that important here, so I will not emphasize too much. But for example, 21 is the code for external walls, 13 is the code for floors on grade, and so on. Now, if we look at one specific macro element, for example, the outer wall, we see that this outer wall can again be subdivided in different parts. So our outer wall, our macro element wall, or our overall element of the external wall, is subdivided typically in a primary layer, the load-bearing part, for example, finishing layers. So for here, for example, you have an outer finishing and an inner finishing, and typically we can also have openings in an external wall. So the different coding will allow you to know what we're talking about. So for example, 21 is a primary part of an element, 41 is the outer finishing, 42 is the inner finishing. If we add all these up, we give it the symbol 21 plus. So it means it's the primary layer of the external wall plus all the additional layers, except for the openings. So the openings, for example, get the code 31. If we have a cost of an element including the windows, we talk about the element 21 plus plus. So it's the primary layer, 21, plus the first plus refers to the inner and outer finishing, and the second plus refers to the openings that are included. So in the beginning, when our building is, when we are in the beginning of the design phase, we typically have costs per square meter of a certain element. So for example, the square meter of an external wall, defining the cost of the full element, including internal and external finishing, because we don't know yet what exact finish will be used. So we take an average cost of that finish. Later on, when the design process evolves and we know exactly which external and internal finishes are used, we can update our unit price, we can more precisely determine the exact cost per square meter of wall. So that is the idea. What we do is we subdivide our building in different elements which have a different function and hence require different technical solutions. For each of these, we will have a cost calculation. The cost calculation of a certain element in the early design phase will be very rough, based on averages, while later on in the design phase, they will be more detailed. They will be more detailed by looking at the different specific solutions chosen for that building, and by hence adding these costs to make a more precise cost estimate. So when talking about functional elements at the highest level, we have a hierarchical structure. So here are the macro elements. So the macro element of outer wall, of the internal floor, and of the roof, including a price, for example, including the openings even, an average amount of openings. Or we can have more precise costs for the different layers and add them up later on in the design process. So when we calculate the cost of a building, when we estimate the cost of a building, what we do is we structure the data in tables at the highest level. Very early in the design phase, we have a building cost calculated in a table where each row of the table represents one macro element. I'll come back to this slide, but I first go to the next to show this. So here what we have is a such table. This is the cost estimate of a building. I have the different codes, so the different macro elements that I'm looking at. I have the different description. For those who don't understand the coding, they can here see the description of the code. We have a certain price, a unit price, and so it is important to define a certain unit, and then I will go back to that. What we see if we want to calculate the cost of a building is that on each line in the table we have a different macro element. So the macro element of outer wall, the macro element of inner wall, and so on. For each of these we will need to have a price. We need to define the cost of that element in the building. And how we do that is in different steps. In the early design phase, we typically have an average cost for that specific element without knowing the build-up. It's just an average cost based on experience. What we do need to define is the unit. Do we know a cost per meter, per square meter, per piece, and so on. So we define the unit price. So for example, for the outer wall, the third row, we have a price per square meter. While for the foundation, for example, we have a price per running meter. For our specific building, we will need to define the ratio, so the amount of that element we have per square meter floor. I'll come back to that in a second. And then we can calculate the price of a certain element per square meter floor. So for example, I know my unit price for strip footing is P2 per running meter. I know I have 0.123 running meter of strip footing per square meter of floor. So my cost for the strip footing per square meter floor is multiplying the price per unit with the unit per square meter floor. And then I get this price per square meter floor. If I want to know the full or the overall cost of the strip footing at building level, I need to multiply this number with the total square meters of floor, which is indicated here. So I have 3,000 square meters of floor. So if I multiply this cost per square meter floor with 3,000 by 3,000, I get the full cost of that element for at building level. Now if I go back, this price per meter strip footing or this P3 per square meter outer wall can be determined in a new table. And now I go back to the previous slide, because at the second level, each macro element, so for example my outer wall, can be summarized again in a table. But now each row of the table is not an element anymore, it's a part of that specific element. So all the work sections, all the processed materials that occur in the element. And by doing that, later on, typically in the design stage, when my build-ups of my elements have been defined, I can more precisely calculate my unit price. And so I can keep my table here, but this unit price will be refined along the design process. And maybe if I also change the layout of my building, the ratio will change, but I'll come back to that. Finally, at the lowest level, the price of each work section can again be determined in a table by now having on each row a cost per material or process that is needed to make that work section. That's the idea of the element method for cost control. So the cost, in this case the investment cost of a building, is seen here. This is my investment cost, which is the sum of all the costs of the elements occurring in my building. And the cost per element is calculated by multiplying the cost of that element per square meter floor by the numbers of square meters I have. And the price per square meter floor of that element is determined by the unit price and the amount of element I have. And that brings us to the concept of the ratios, because this amount of element per square meter of floor is called a ratio. So if I go back to my element table, I have, this is a table at building level. Each row is one specific element in my building. I have on the one hand the price, the cost per unit of element. And this is determined by the choices you make, the technical solutions for a specific element you make. And hence is very much determined by the quality you want to achieve. Secondly, I don't have enough by knowing the price per unit. I also need to know how much of each element I have per square meter floor, for example, or in total. If I look at it per square meter floor, we call it ratio. And this amount is determined by the layout of my building. So for example, if I have a very incompact building, I will have a lot of external wall. If I have a lot of external wall, although my price per square meter is maybe not high, if I have a lot of it per square meter floor, my costs for external walls will be high. So I could change my layout then to reduce the amount of external wall I have. So by splitting up in an element table the unit prices and the amount of a certain element per square meter floor, so the layout influence, you can really, it enables you to detect the cause of a high cost. Either it is because you chose a very expensive technical solution, or it is because of a layout choice. So the element method of cost control does not, or cost estimation, does not only show you which of the elements contribute most to the total cost, it also allows you to detect if that is caused by a high unit price because of a complex technical solution or very expensive materials you chose, or if it's caused by the layout, by the fact that you have a high amount of a certain element. Now let's go a bit further into detail to explain you this concept of ratio. So for example, we have three buildings. We have a detached building, two detached buildings, one with a square floor plan, one with a rectangular floor plan. And I have also a terrace building. The floor area of my first building is 10 by 10 meters, so I have a building of 100 square meter floor area. I have 4 external walls, 1, 2, 3, 4. Each external wall is 10 meters by 3 meters, so 30 square meter for each external wall, and I have it 4 times, so I have 120 square meter of external wall. The ratio of my wall is the 120 square meter divided by 100 square meter. So I know how much external wall, square meters of external wall I have per square meter of floor area. So it's 120 square meters divided by 100 square meters. It's 1.2 dimensionless because it's square meter divided by square meter. So it shows that I have more external wall than floor area, 20% more, it's 1.2. If I look at my second building, I have a floor plan of 20 by 5 meters, 100 square meters. So it's the same floor area as the first building. My external walls are again 4 facades, so I have 4 external walls. My front facade is 20 meter by 3 meters, so 60 square meter, and my back facade as well. So 2 times 60 square meter. My side facade is 5 by 3, 15, and on the other hand as well 15. So my total amount of external wall is 150 square meter. I can immediately see that I have more external wall in the second case than in the first case. Why? Because my square meters of floor are actually the same. So in this case, it would not be really needed to calculate my ratio because my floor area is identical. So I can easily compare my external wall, amount of external wall that is different. If I calculate it anyway, it confirms what I said before, because 150 divided by 100 is 1.5, which is higher than in the first case. Now I have a third building, which is a terrace building, a building between other buildings. I have a facade of 5 meters wide, and I have 3 floors, each more or less 3 meters high, so I have a total height of 10 meters. My building is 10 meters deep. The floor area is now 5 meters by 10, 50 square meters for one floor, but I have 3 floors now. So I have in total 150 square meters of floor area. My external wall area is now limited because I have only 2 external walls, one in the front and one in the back. My front facade is an external wall of 5 meters by 10 meters, is 50 square meters, and the same for the back facade. So I have 100 square meters in total. Now in this case, I need to calculate my ratio of the wall in order to be able to compare how the layout and the building typology of this building compares to the others, because my floor area is now changing. I see here that my ratio of the wall is 0.67. So it means that if my external wall would be the most expensive element of my building, it would mean that this building will lead to a lower investment cost, because the amount of external wall that I need for this building is lower than for the others. If I compare these two, I know that I will have a higher cost for external walls in this building than in that building, because if the technical solution is identical, so my unit price, my price per square meter wall is identical, I will have a higher cost in this building because I have a higher ratio. So the lowest one has the lowest ratio, and if an external wall is very expensive, it means that this layout is preferred from an investment cost perspective. And that is hence what the ratio or the element method with ratios does. So for each project we can make such table, and that is exactly what you will do for your building. We will have an overview of all the elements that are occurring. We will take an average price per unit of element. But what is important is that we will determine how your design, how your project influences the different ratios. So what the consequence is of a certain layout choice on the amount of the different materials occurring in the building. By knowing the price and by knowing the ratio, we can calculate the price of a specific element per square meter floor area. And as the different floor areas of your buildings will differ, it is important to have this cost per square meter floor, because then we can compare the different projects. It's very difficult to compare the cost of different projects if the surface, the floor area differs, because then there's no way of comparing. While if we look at the cost per square meter floor, we can compare the different projects, although the size is different. So this kind of table will be derived for the different projects, and each of your projects will lead to a different table and hence a different cost per square meter floor. In the next step, but it's not what we're going to do, but in the next step, the prices for each of the elements, the unit prices, which we now will consider as a fixed price, it will be the same for all of you to just focus on the layout influence on the cost. So these unit prices could be calculated, refined in future if you want to calculate a more exact cost of your building. And how do you do that? Well, you draft again a table on the lower level in the same way. For each element, you define the different work sections, different process materials. You look up the cost of that processed material. You define how much of that material you have per unit of element, and you can calculate for that for each work section the cost per square meter of element. If you add them all up, you have a cost per square meter element or per unit of element, which you can replace, refine your table. And that is exactly what is being done in a design process. In the beginning, you take an average price based on the experience you have of each element, but later on in the design process, you can refine your table by refining the unit prices. So this, to show it in more detail, each of these unit prices are refined in a subtable where you define the cost per unit element by looking at the different work sections. And with this, I will end the first video of the cost estimation at building level.